So this example is going to be a problem where we set up an integral with a slightly different orientation than we've been using, and that's specified in the problem. That's not to say that you couldn't orient this the way that we have and still work it out as this being surface 1 and surface 2 and integrating over surface to surface vertically and using this region down in the bottom here as our integral. It could be done very well that way, but in this case we've been asked specifically to integrate with respect to x, then y, then z. So if we're thinking about setting up our triple integral here, this is going to be a triple integral over the solid E of x, y, z dv. And again, we've been asked to set that up in a specific order, x first, then y, then z. So this is what we're looking for, and we're integrating over our solid E. I'm going to split this up as I have in the other videos that I've made and just draw out that these last two integrals are going to be the integral over the region D, and this integral in the inside is going to be our surface to surface. And we'll set it up that way. And our surface integral then has to do with x, so we need some x bounds on that. The y bounds and the z, the yz here is going to be this region D that we're talking about. And we can see that region over on our graph as this vertical plane that lies in the yz plane. So that then becomes the region D that we integrate over. Our surface to surface then is represented by the arc that's going vertically here in behind. And again, the region D now becomes the other surface. Again, that's the range of values that x would travel through going across from one surface to the other. So let's extract out what those equations are. In the case of the arc, that's given up here as y equals the square root of x. But again, I'm looking for a bound that is specifically the x piece of that, so we need to reverse this, find its inverse, and write this as x equals y squared. And of course, we're only taking really part of that, but that's okay. We'll take the whole function to represent the upper surface of our integral. And we also have the lower surface, which is given again as this vertical plane here. And given that it's the yz plane, that is effectively saying that x is equal to 0. So now I've got my bounds for x. 0 less than x less than y squared. So those will go on our integral over here as the integral 0 to y squared. So looking at where we are right now, we've got the double integral over the region D, and our integral from 0 to y squared of x, y, z dx, and I'll throw a dA on the back. But we've been specifically asked in this problem again to do this as dy dz. Okay, so let's see if we can get the rest of our bounds here. We're looking at the region D, which is again this vertical plane here. And we can see across the line here at the bottom, we've got y going from 0 to 2. And vertically we can see that z goes from -2 to 1. So -2 less than z less than 1. So now I've got my bounds for y and my bounds for z. We can actually see why this turns out to be a good way to do this problem, particularly because the region that we end up with here, the projection into the yz plane of this surface, actually ends up being a rectangle, which makes it really nice to compute because then we end up with just constants for our limits. So let's finish out our integral here in terms of our setup. I'm going to take the integral now, and again, we've been asked specifically to do this as dy and then dz. So our outer integral is going to be the z's, which we saw went from -2 to 1. And then the integral for the y bounds, 0 to 2. And again, we've got our innermost integral being the surface to surface going from z up to y squared. And our integrand, x, y, z, dx, dy, dz. The hard part, in my mind, is generally done at this point because we've already set up the integral. And the integrand is not terribly complex, so we should be able to work through this pretty quickly from here. I'm going to let you guys finish that out and see if you can get it right.